Crash Course Instrumentation, Episode 4 in our Instrumentation Fundamentals series, Reactor Temperature Control. Welcome back to Crash Course Instrumentation. In this Episode 4 of our Instrumentation Fundamentals series, we're diving into a control loop that's critical for process chemistry and product quality: the chemical reactor temperature control system. Why is temperature so important in reactors? Because chemical reactions are highly sensitive to heat. Too cold? The reaction slows down or stops. Too hot? You risk unwanted side reactions, or worse, a runaway reaction that becomes dangerous. That's why precise temperature control isn't just a preference, it's a must. Let's break down the control loop for a typical temperature control system. 1. Temperature sensor, RTD or thermocouple. This measures the internal temperature of the reactor. It sends a signal, often 4 to 20 milliamperes, representing the process variable, or PV. 2. Controller compares the PV to the set point, SP. If there's a difference, it calculates the error and generates a controller output, CO. The controller often uses PID logic, proportional, integral, and derivative actions, to deliver a smooth, stable response. 3. Heating-cooling system, final control element. This could be an electric heater, a steam jacket, or a coolant flow valve. The controller output tells the system how much to adjust heating or cooling. In an exothermic reaction, where the process generates heat, the controller may need to remove energy by opening a cooling valve. In an endothermic reaction, the controller must add heat to maintain the proper rate. Many modern systems use smart temperature transmitters that convert sensor signals into robust, noise-resistant analog or digital outputs. These can be monitored remotely through a DCS, distributed control system, or a SCADA, supervisory control and data acquisition, system. Quick comparison. DCS is typically used in large continuous process facilities like chemical plants or refineries. It provides tight integration, high reliability, and real-time control right at the process unit. SCADA is more common in geographically distributed systems like water treatment or power grids. It excels at central monitoring and supervisory control from a remote operations center. For example, a DCS might run the reactor PID loop locally and trend internal temperatures in real time. A SCADA system might allow operators 20 miles away to monitor alarms and manually start a backup pump. Example: let's say your reactor has a set point of 150 degrees C. A thermocouple senses that the process is drifting up to 153 degrees. The controller kicks in, sending a signal to increase cooling. Once the temperature drops back to set point, the system stabilizes. All of this happens in real time, automatically. Temperature loops like this are textbook examples of closed-loop control, a foundational concept in instrumentation. Historical context. The first temperature control loops were developed in the early 20th century, when chemical manufacturing scaled up dramatically. Steam jackets and mercury thermometers were common. By the 1930s, pneumatic PID controllers emerged, followed by analog electronics in the 1960s and digital systems in the 1980s. Each generation brought greater accuracy, faster response, and better safety. On the physics side, this process highlights key thermodynamic principles. Heat capacity of materials affects how quickly temperature changes. Thermal lag can cause oscillation if not properly tuned. PID tuning helps minimize overshoot and maintain stability. You'll encounter reactor temperature control loops in industries like pharmaceuticals, plastics and polymers, petrochemicals, food processing. If you understand how this loop works, you can troubleshoot heater faults, tune controllers, and optimize energy use. This episode is based on lessons in Industrial Instrumentation by Tony Kuphaldt. You can read the full open-source version at the link below. Like, subscribe, and join us as we continue exploring the systems that make modern industry possible. Explore the full text. https://biblio.org Kuphaldt, Socratic model, Watch all episodes. www.youtube.com/Crash Course. Instrumentation. Join the discussion. www.facebook.com/groups/Crash Course Instrumentation.